word this part. Okay, so this is going to be very short. It's a brief introduction. Then we're going to go into chapter 3, section B, immediately after that. So it says, what is an order of magnitude? Explain why such an estimate can be useful, even though it may be as much as 10 times too large or too small. Well, for the support part, I'm going to be teaching on this in just a minute. But for the support part, the definition is going to be, the right answer is C. Okay, an order of magnitude estimate specifies only a broad range of values, usually within 1 or 2 powers of 10. These estimates are useful because they provide a way to easily tell the difference in groups of values such as populations. And I know that on the support, it gives you multiple chances. So that's kind of just a brief introduction to that definition. So number 2 says, determine whether the statement makes sense. If the statement is possible, then it makes sense. If it is clearly impossible, it does not make sense. So last year, this is a statement we're trying to say, well, does this even make sense? Last year, my heart beat 4 times 10 to the 7th time. Well, first off, you're going to have, this is scientific notation. So you start with the number 4, and right now 4 has a decimal place that would come immediately after the 4. And this 7 right here is telling me I should move my decimal place over 7 times. So 1, 2, 3, 4, 5, 6, 7, and my decimal would go right here. And all of these places in the middle of that would get zeros. So if I wrote this number down, and that's why we use scientific notation, because just then I was having difficulty, like, how many zeros is it? Adding the commas helps a lot with me counting the zeros, but after the decimal place, we don't have commas. So if something's really, really small, scientific notation is really good for that. So this number is 40 million. So basically we're asking, is it reasonable to think that your heartbeat would beat 40 million times a year? Well, I don't know, but I could think about, come up with an approximation, right? Everybody's heart's different, but in a minute, we would think our heart beated probably what? Just resting, probably have a resting heartbeat of like 60 beats a minute. I'm not a scientist, but I'm just saying, like something around there. If I felt my pulse, like around 60 beats per minute. Some people would be faster or slower, but okay. So if I want to know if this is reasonable, that this many times it beats in a year, well, I need to know how many minutes are in a year, right? Well, here's what I know about minutes. I can say, I can multiply by 60 because there's 60 minutes in an hour, right? I'm trying to get to a year. I know how many hours are in a day, so I can multiply by 24 hours in one day. Okay, and then finally, I know how many days are in a year, and I'm not going to use the 365 and a fourth. We're just trying to see if this estimate. So 365 days in a year. Could I line this up like we did the conversions on chapter 2? Absolutely. I just didn't do it. Like we could make that little chart where we start with 60 beats, 1 minute, right? And then the next one would be 60 minutes because we want the minutes to cancel out in an hour. And the next one would be 24 hours in a day. And we would get the stuff to cancel out like we want it to. Maybe I need to, she said about 60 beats every 1 minute. And then we would have 60 minutes in 1 hour. Then we had 24 hours in 1 day. And then we had 365 days in 1 year. And that's what we're trying to come up with. We're trying to find beats per year. Okay, so The minutes canceled out, the hours canceled out, the days canceled out, and I'm left with beats per year. So I would take these numbers and just multiply them. So 60 times 60 times 24 times 365. That is getting me $31,536,000. I think that, and our estimate was, so 31,536,000. Our estimate was 40 million. I think that's kind of that's kind of reasonable to me, especially if somebody's heart beats a little bit better. But 40 and 31, you want to look at the first two, 40 and 31 in the same place. Yeah, that's okay. That's a reasonable estimate. Okay. So, oh yeah, absolutely. So write the number in scientific notation. Making sure their answer agreed with mine. Write the number in scientific notation. So right now, these are going to go kind of fast. Right now, our decimal is right here. So to get it in scientific notation, here's the thing. You need the number in the front to be between 1 and 10. So I want to move this decimal place 1, 2, 3. 351 is not between 1 and 10, so I would move it again. That's 4 times. Is 35 between 1 and 10? No, we got to move it one more time. And so we would get 3.51 times 10 to the however many times you move that decimal. And it looks like we've moved it 5 times. So A. Okay, 2 times 10 to the 6th. We're going to start out with 2, put our decimal here. This is telling me when it's a positive 6, you're going to move it to the right 6 places. So 1, 2, 3, 4, 5, 6. Decimal place is going to come here, and in between get zeros. So we basically have 6 zeros. So 2 million. Okay. 6 times 10 to the negative 5th. Now that one's different because now we don't have a positive exponent, we have a negative exponent. So we don't move our decimal to the right, we move it to the left. It's actually going to make the number smaller. So we're starting out with 6. We know our decimal place is here. If we move our decimal place 5 times, we're going to have, so our new decimal place is right here. 1, 2, 3, 4, and then the 6, we had to move our decimal place back 5 times. So 0.00006. And you can tell right now that this is difficult to count. That's why people write things in scientific notation. Those zeros are kind of crazy. Last example on the support. It says write the number in scientific notation. And we have a decimal number. So bear with me because I'm trying to, it looks like we've got 6 zeros after the decimal. I don't care about the 0 in front of the decimal. So 1, 2, 3, 4, 5, 6. And you can see that I struggle with that. If it was in scientific notation, I would know exactly how many zeros were and I wouldn't have to count, but we're going to move it. 1, 2, 3, 4, 5, 6, 7. Now hold on, I need the number to be between 1 and 10. So I need to stop at the 2 because if I move it to the 0, we're going to have 20, and 20 is not between 1 and 10. So we need to back up and stop at 2. 3, 4, 5, 6, 7 to get the decimal right here. So 2.04 times 10, and we moved it and we made the number smaller. When you make the number smaller, you're going to have a negative exponent. -7. So we moved it 7 times. Okay, so that's your support. Do your support before you do your assignment on in chapter 3, section B.